Settle into a comfortable position and let your attention rest lightly on the sound of these words. You do not need to memorize every detail. Let the larger pattern become familiar as we move along. Tonight, we are exploring the paper. Attention is all you need, and the model it introduced, the transformer. The paper asks whether a machine can understand and generate language without carrying information through a long chain of recurrent steps. This matters because language contains relationships that may stretch across an entire sentence, while the hardware used to train neural networks works best when many calculations can happen together. The transformer's answer was to place attention at the center of the architecture. Consider two simple sentences. The animal did not cross the street because it was tired, and the animal did not cross the street because it was flooded. In the first sentence, the word "it" probably refers to the animal. In the second, it probably refers to the street. The word itself is unchanged, but the surrounding context changes its meaning. A useful language model must therefore do more than identify individual words. It must learn which parts of a sentence help explain one another. A sentence is one example of a sequence, an ordered collection of elements. In language, those elements may be words, punctuation marks, or smaller pieces of words called tokens. The order is important because rearranging the same tokens can change the meaning completely. When a model learns patterns in ordered information, it is performing sequence modeling. When it converts one sequence into another, as in translating an English sentence into German, it is performing sequence transduction. Before the transformer, many of the strongest sequence models were recurrent neural networks. A recurrent network reads a sequence one position at a time. It combines the current token with an internal state that carries information from earlier positions, then passes an updated state forward. You can imagine a message moving through a line of people. Each person receives a summary, adds one new piece of information, and passes the revised summary to the next person. This naturally preserves order, and improved recurrent designs, such as long short-term memory networks, were created to help important information survive across more steps. The same step-by-step structure, however, creates a computational limitation. The second position depends on the first, the third depends on the second, and the process continues in order. Even with many processors available, the positions inside one sequence cannot all be handled at once. It is like hiring many workers but requiring them to perform one shared task in a strict line. The model can still learn effectively, but it cannot fully use parallel computation during training. Sequential processing also lengthens the path between distant pieces of information. If a word near the end of a sentence depends on something near the beginning, the relevant signal must travel through every intermediate recurrent step. Better memory mechanisms reduce the chance that it will be lost, but they do not shorten the path. This is the difficulty of learning long-range dependencies. Information that belongs together may be separated by many computational transitions. Convolutional neural networks offered another approach. A convolutional layer can process many positions in parallel, usually by examining a small local neighborhood around each one. Stacking several layers allows information to spread across a wider region. This improves parallelism, but distant positions may still require several layers before they can interact. Recurrent networks move information through time, while convolutional networks move it through layers and local windows. These limitations suggest a different design. Rather than making information travel through a chain or a succession of neighborhoods, perhaps each position could look directly at the positions relevant to it. This is the role of attention. Attention allows a model to assign different degrees of importance to different pieces of information and then combine them according to that importance. When interpreting one word, the model does not have to treat every other word equally. Attention was already part of successful translation systems before the transformer. A recurrent encoder would process an input sentence, and a recurrent decoder would use attention to consult useful parts of that encoded input while generating the translation. Attention helped the decoder decide where to look, but the underlying sequence processing was still recurrent. The transformer changed that relationship by asking whether attention could become the main method for connecting information, rather than an additional feature attached to recurrence. The form of attention used within a single sequence is called self-attention. In self-attention, the representation of each position is allowed to gather information from other positions in the same sequence. A word near the end can connect directly with a word near the beginning in one layer. Returning briefly to the earlier example, the position representing it can examine both animal and street, along with words such as tired or flooded. The surrounding pattern helps determine which connection should matter more. Self-attention describes the goal, but the model still needs a mechanism for deciding which positions are relevant. The transformer expresses this mechanism using queries, keys, and values. A library search offers a helpful analogy. Your request describes what you are looking for and acts like a query. Each book has identifying information that can be compared with the request, acting like a key. Once a useful book is selected, the content you retrieve acts like the value. Inside the actual model, queries, keys, and values are numerical vectors created from token representations through learned transformations. The query represents what a position is seeking. A key represents the features by which another position may be matched. A value carries the information that position can contribute if the match is strong. The analogy describes the roles, while the literal mechanism consists of learned vector operations. To measure a match, the transformer compares a query with each available key using a dot product. A dot product turns two vectors into a single score. In the model's learn representation space, a larger score generally indicates greater compatibility between what the query seeks and what the key offers. Performing this comparison against every key creates a set of relevant scores for the current position. The raw scores must then become usable weights. The model passes them through a function called softmax, which converts them into non-negative values that add up to 1. A position with a large weight contributes strongly, while one with a small weight contributes little. The attention output is formed by taking a weighted combination of the values. In plain language, the model measures relevance and blends information in proportion to the relevance. The paper adds one important adjustment to this calculation. When query and key vectors have many dimensions, their dot products can become large in magnitude. Softmax may then produce extremely concentrated weights, placing the model in a region where gradients become very small and learning becomes more difficult. To control this effect, the scores are divided by the square root of the key dimension before softmax is applied. The result is known as scaled dot product attention. One attention operation gives the model one learned perspective on the sequence, but language often contains several kinds of relationships at once. A word may be linked to its subject, a nearby phrase, a distant reference, and the wider meaning of the sentence. Combining all of those patterns in one attention distribution may blur useful distinctions. The transformer therefore uses multi-head attention, allowing several attention operations to run in parallel. Each attention head receives its own learned projections of the queries, keys, and values. One head may become useful for nearby grammatical relationships, while another may connect information across a longer distance. A different head may respond to phrase boundaries or semantic relationships. These roles are not assigned by hand. They emerge during training. The outputs of the heads are joined and transformed into one combined representation. In the original transformer, the heads operate on smaller representations, so several of them can run without making the total cost dramatically larger than one full-sized attention operation. The purpose is not simply to repeat the same calculation several times. It is to provide distinct representational spaces in which different kinds of compatibility can be learned. Multi-head attention lets the model examine the same sequence from several useful angles at once. Attention can identify relationships, but by itself, it does not contain a built-in sense of order. If the token representations were rearranged, pure self-attention would still see the same collection unless positional information were added. Recurrent processing naturally reveals which token comes next, and convolution has an organized local structure. Since the transformer removes both mechanisms, it must introduce order deliberately. Each token first receives an embedding, a learned numerical representation of its identity and use. The model then adds a positional encoding to that embedding. The original paper used sine and cosine functions with different frequencies, giving each position a distinctive pattern. Some dimensions change slowly across the sequence, while others change quickly. Together, they allow the representation to carry information about both token identity and position. The exact trigonometric equations are less important than their purpose. A token should tell the model not only what it is, but also where it appears and how far it may be from another token. The researchers also tested learned positional embeddings and found that they performed almost as well. They selected the sinusoidal version, partly because its regular structure might generalize to sequences longer than those used in training. With token identity, position, and self-attention in place, we can follow information through the full architecture. Like many earlier translation systems, the transformer has an encoder and a decoder. The encoder turns the input sequence into context-rich representations. The decoder uses those representations, together with the output generated so far, to produce a new sequence, one token at a time. In the original model, the encoder consisted of 6 similar layers. Each layer contained a multi-head self-attention sublayer, followed by a position-wise feed-forward network. Self-attention lets each position gather information from other positions. The feed-forward network then transforms the resulting representation separately at every position, using the same transformation throughout that layer. Attention mixes information across the sequence. The feed-forward network refines what each position has received. You might picture the attention operation as a discussion among the tokens. After the discussion, each token privately processes the information it gathered. This is only an analogy, but it captures the division of labor. The attention sublayer handles relationships between positions, while the feed-forward sublayer performs a nonlinear transformation at each position. Different encoder layers repeat this pattern with their own learned parameters, gradually building richer representations. Deep stacks of transformations can make earlier information difficult to preserve, so the transformer uses residual connections. A residual connection adds the original input of a sublayer back to its output. It is like keeping the earlier version of a draft while adding a revision instead of replacing the original completely. This creates a more direct route through the network and makes deep architectures easier to train. The original transformer also applies layer normalization after each residual addition. Layer normalization keeps the scale and distribution of values within a useful range, supporting more stable learning. Residual connections preserve access to earlier information, while normalization keeps the evolving representation controlled. These operations surround both the attention and feed-forward sublayers throughout the encoder and decoder. By the top of the encoder, each input position represents more than its original token. It also contains context gathered from other relevant parts of the sentence. The encoded representation of a verb may include information about its subject, while the representation of a pronoun may reflect the noun it probably refers to. The encoder's job is not to produce the final translation. It creates an interconnected representation of the source that the decoder can consult. The decoder must solve a different problem. It needs to understand what it has already generated, remain connected to the input, and predict what should come next. Its layers, therefore, contain 3 main sublayers rather than 2. The first is masked self-attention over the output sequence so far. The second attends to the encoder's output. The third is the same kind of position-wise feed-forward network used in the encoder. The word masked is important because training provides the model with an entire correct target sentence. Without a restriction, the decoder could examine future target words while learning to predict them. That would be like revealing the answer before asking the question. Masked self-attention prevents each position from attending to later output positions, so a prediction can depend only on the tokens that have already appeared. Imagine the target sentence written on a page with the future portion covered. The decoder may read the visible beginning, but not what comes later. Mathematically, the mask makes forbidden attention connections unusable before softmax calculates the weights. This maintains the autoregressive structure of generation. Each token is predicted from the output history available at that moment. Masked self-attention tells the decoder about the partial output, but translation also requires information from the original input. The decoder, therefore, uses encoder-decoder attention, often called cross-attention. Here, the decoder supplies the queries, while the encoder's final representations supply the keys and values. The decoder can search across the entire input for whatever source information is useful for the next output position. The two attention operations answer different questions. Masked self-attention asks what has already been generated. Cross-attention asks which parts of the source should guide the next prediction. A decoder position producing a translated verb may focus on the source verb and its subject, while another position may consult a noun phrase elsewhere in the input. The precise alignment is learned from data rather than specified by a fixed rule. After passing through the decoder's stacked layers, the final representations are transformed into probabilities over possible next tokens. Softmax, again, converts model scores into a probability distribution, this time across the output vocabulary. A decoding procedure chooses among those possibilities, adds the selected token to the output, and repeats the process. The output grows step by step until the sequence is complete. The full architecture now forms a connected picture. Input tokens receive embeddings and positional information. Encoder self-attention gathers context, and feed-forward networks refine it. Residual connections and normalization support the deep stack. The decoder uses masked self-attention to understand its own history and cross-attention to consult the source, then produces probabilities for the next token. The title, "Attention is all you need," is intentionally bold, but it does not mean that attention is literally the only calculation in the model. The transformer also requires embeddings, positional encodings, feed-forward networks, residual connections, normalization, and output transformations. The title emphasizes what was removed. Recurrent and convolutional layers were no longer needed as the main machinery for sequence interaction. Attention became the central method for connecting positions. This design offered three major advantages in the paper's comparison. First, encoder positions could be processed in parallel rather than one after another. Large matrix operations could calculate attention for many positions together, matching the strengths of modern graphics processors. Second, any two positions could interact through a short path in one self-attention layer. Third, the interaction pattern could change according to the content instead of being limited to a fixed local window. The short path is especially important for long-range dependencies. In a recurrent network, two distant positions may be connected through many sequential updates. In a convolutional model, they may require several stacked layers. With full self-attention, each position can directly consider every other position. This does not guarantee that the model will learn every distant relationship, but it gives learning signals a much more direct route. The architecture also supports a degree of interpretability. By examining attention weights, researchers can observe which positions particular heads emphasize. The paper showed examples in which different heads appeared to follow syntactic or semantic patterns. Attention weights should not be treated as a complete explanation of everything a model knows, but they provide a visible structure that is less obvious in a single recurrent, hidden state. The researchers tested the transformer primarily on machine translation. Translation quality was measured with the BLEU score, a standard metric that compares machine translations with human reference translations through overlapping words and phrases. The larger transformer reached a score of 28.4 on English to German translation, exceeding the previously reported systems included in the paper's comparison, including model ensembles. It also produced a strong English to French result, while using substantially less training computation than several earlier approaches. Training efficiency was part of the result, not merely an implementation detail. The base model was trained in roughly 12 hours on the hardware used in the study, while the larger models took several days. The exact equipment is less important than the contrast with earlier systems that required greater training cost. The experiment showed that removing recurrence could improve practical efficiency without requiring a reduction in translation quality. The paper also tested English constituency parsing, a task that identifies the nested grammatical structure of a sentence. The transformer performed competitively, even though the architecture received limited task-specific tuning. It worked with both larger and more restricted training settings. This suggested that the model was not useful only for one translation benchmark, but could represent structured language more generally. Additional experiments explored which design choices mattered. A single attention head performed worse than a stronger multi-head configuration, supporting the value of several representational perspectives. Larger models tended to perform better, and dropout helped prevent overfitting. Learned positional embeddings and fixed sinusoidal encodings produced nearly identical results in the reported comparison. These experiments supported the overall design, while also showing that some details had viable alternatives. The transformer's strengths come with a significant cost. Full self-attention compares every position with every other position. As sequence length increases, the number of pairwise comparisons grows quadratically. Doubling the sequence length produces roughly 4 times as many comparisons. This becomes expensive for very long documents and for dense inputs, such as high-resolution images, long audio streams, or video. The original paper already identified restricted or local attention as one possible response. Instead of allowing each position to attend everywhere, the model could examine a smaller neighborhood. This lowers computational cost, but gives up some direct global connections and increases the path between distant positions. The design therefore involves a trade-off between global access and efficiency, a trade-off that later research would continue to explore. There is also an important difference between training and generation. During training, many positions can be calculated in parallel because the target sequence is available and masking controls which information each position may use. During autoregressive generation, however, The decoder still produces one new token after another. The next token cannot be finalized until the previous output is known. The transformer greatly reduced sequential computation inside the architecture, but it did not make ordinary autoregressive generation fully parallel. The larger implication of the paper was that attention could serve as a general method for organizing relationships. The authors anticipated applications beyond text, including images, audio, and video. In each case, the same broad question appears. Which elements should influence one another, and how directly should they be connected? The original work did not solve every version of that problem, but it established an architecture flexible enough to make those questions approachable. The transformer can now be held as one connected idea. Earlier sequence models carried information through recurrent steps or local convolutional layers. The transformer instead allows positions to gather relevant context through self-attention. Queries express what a position seeks, keys help measure compatibility, and values carry the information that is combined. Scaling stabilizes the scores, multiple heads preserve several perspectives, and positional encoding restores order. The encoder uses these tools to build contextual representations of the input. The decoder uses masking to respect the boundary between past and future, then uses cross-attention to remain connected to the source. Feed-forward networks refine each position, while residual connections and normalization support the layered structure. The result is a sequence model that shortens the path between distant information and allows much more parallel training, while accepting the growing cost of full attention on long sequences. You do not need to keep every technical term active in your mind. It is enough to remember the central shift, meaning no longer has to travel through a long chain before related information can meet. The details can settle quietly now, while the broader structure remains familiar. Attention identifies the connections that matter, and the transformer builds its representations from those learned relationships.